heights of the flows. And so in some places it's relatively high, in some places it has troughs caused by waves. And so when we talk about free surface flows, many of the tenets that we've dealt with, such as using Bernoulli, etc., and conservation of momentum equations apply. But the water in this case has, if you like, an extra degree of freedom. So if you have flow in a pipe, it has to fill the section of the pipe, and it can't be any larger cross-sectional area than that, and so that's constrained. But if it's flowing in a channel, then you could imagine that it could either flow very quickly and be quite shallow, or flow much more slowly and be deeper, and still have the same volumetric flow rates. And so what we'll find out today is that we can rationalize why you get waves and hydraulic jumps and all these weird and wonderful phenomena in open channel flows. And it's because you have this kind of unknown parameter, which is that the surface gets to set its own height in some respects, relative to some laws. And so that's kind of where we're going with this. All right. So this is the plan for today. And so we'll talk a little bit about the flow classifications that we've alluded to on these YouTube videos. We'll talk about defining hydraulic radius, and then we'll skip to talking about uniform flows, and this is the stuff that we want to spend a little bit of time on. And then rapidly varying flows are the ones that we just looked at. We'll deal with that in much less detail, depending on how much time we have today. So that's the plan for today. So we've already alluded to this, the difference between open channel flows and pipe flows is really not so much the fact that the pipe is only half full. Of course, you could imagine an open channel flow being where you have a pipe which is half full and is flowing with an airspace in it. But the main difference is that the main factor driving flow is only gravity. And so you could imagine that if you had a big pressure that you applied at the upstream location, which was P1, which was just a large pressure, and you had a small pressure at the downstream portion, then if the top part is air-filled and the bottom part is liquid-filled, then all the flow would just be in the air that would be above that, and it would travel and short-circuit the system. And so that's not really what we're talking about. The issue is that in open channel flows, the pressure differential that you can have between the upstream and downstream is really going to be driven by just gravity. The only driving feature is gravity. And so that can also be the case in closed pipe flows as well, right? You can imagine this pipe being completely full, as for instance a culvert would be in times of flood spate, and that would also mean that you can't get a very large pressure gradient that's driving. So the main deal dealing with pipe flows is that the main component driving flow is gravity, and as a result, one of the important parameters that deals with that is the Froude number, which is of course the ratio of the flow velocity to the wave velocity. And so we'll deal a little bit with that. We talked in pipe flows that the behavior of the flow regime was a big factor. So we talked about these two regimes, in closed flows and also in external flows. And that is at low Reynolds numbers, then viscous effects are important. And therefore viscous drag and viscous lift are important at low Reynolds numbers, like the Stokes settling problem we did. And at much higher flow rates, the Reynolds number is high and the friction factor remains constant. And most of the drag or lift or the friction that occurs in pipes is due to momentum changes and turbulence, development of turbulence. So we have those two regimes. And those two regimes exist also in pipe flows. You can also index open channel, I didn't mean pipe flows, I meant open channel flows. And I don't know why it is, but for some reason we use a different characteristic length, but we use the same indexing parameter. So the indexing parameter for transitions from laminar flow to turbulent flow is still the Reynolds number. It's still a dimensionless number which involves a velocity, a density of the fluid, and a viscosity of the fluid. But now the characteristic number that's used in this is, instead of being the hydraulic diameter, which it was for pipe flows, is actually, we use the hydraulic radius. And so by definition, the hydraulic radius is just the ratio between the cross-sectional area of flow divided by the perimeter. So for a pipe, of course, this would be the perimeter for a pipe. And this would be the area, just like we talked about for a pipe flow. Oh, I guess, but the other component that we should also think about is that in an open channel, then the area would be this, but the perimeter would only be the wetted perimeter, right, which is just this part here. So it's a little bit different from a fully filled pipe. So if the pipe was half filled, then of course it would also look like this, and this would be your area, and this would be your perimeter. So you can use it. So you just need to get used to thinking in terms of that. So hydraulic radius is just defined as the ratio of the area to the perimeter, as opposed to the hydraulic diameter, which is equal to 4 times the area over the perimeter. And so if you identify the fact that the radius is a quarter of the diameter, and you substitute in for the diameter here, then you can use this same classification of Reynolds number in that you'd expect the Reynolds number that gives you turbulence is going to be a quarter of the one that gives you turbulence for pipe flow where you're using the diameter, right? So if you use the diameter, we knew that the transition from laminar, which was less than 1,000 or 2,000, to transitional flows and then to turbulent flows were these numbers, right? Remember the chart that we had, the Moody chart. This was Reynolds number, this was friction factor, this was 64 over Reynolds number for a pipe, and these are all the different values for relative roughness. This region, and you remember these are all kind of coming off here and doing this. So this was kind of a transitional regime. So what was this? This is 2,000 in terms of this. This is roughly 4,000, and this is turbulent and laminar, right? That's what we're referring to. And so the transitions to these were in terms of these particular numbers. If you define the Reynolds numbers in terms of a hydraulic radius, you'd expect that they would scale to a factor of 4, and you'd get exactly the same behaviors. But now, because you're using a Reynolds number that's defined relative to the hydraulic radius, then these would scale, these would be a quarter of the other numbers. Right? So that's basically the deal. It turns out that we don't have to worry too much about that, because if we believe that this is the transition, say 500 to 1,000, if you're beyond 1,000, then you're in this regime where you're turbulent. You can do a quick calculation for an open channel with the hydraulic radius, and if you use density of water, viscosity of water, hydraulic radius for this is a tiny little stream, right? 10 feet wide and a foot deep. You can calculate the hydraulic radius. Hydraulic radius, the area, is going to be 10 by 1, so that's this. The perimeter is going to be 1 plus 10 plus 1, which is 12. And if you do the calcs for this with the viscosity of water in these English units, I guess that's right, you find out that the Reynolds number is something like 100,000, is that right? Yeah, 100,000. So it's 10 to the 5, so it's turbulent. And so all the cases that we'll look at are basically for magnitudes of behavior where the flow is turbulent. So we don't really have to worry about these cases where we have magnitudes less than this, and where we'd have to worry about friction factors which are a function of Reynolds numbers. We'd expect that the values of the friction factors that we use to define the drag, if you like, on flow will all be constant, and they won't change with the flow velocity. So that's one simplification that comes out of our view of this thing. The second item is that when we looked at those videos, we saw that we had, in the terms of fluid mechanics, those flows on the New River would be what are referred to as rapidly varying flows. And so you can imagine a variety of different flow regimes where you have water that's almost static, comes out of the bottom of a sluice. We've talked about free jets. For some reason, it miraculously changes from this very fast and shallow flow regime into a slower but much deeper flow regime. for some reason that we'll maybe allude to. And also cases where you can imagine, slow-flowing rivers at the ends of their course as they go into the sea, where you don't see any of these effects going on at all, but you just see this kind of sedate, uniform march towards the ocean. And so, in this vein, we can define the flows mainly in terms of a classification which relies on two things. It relies on the slope of the bed on which the flow occurs, and it relies on the slope of the water surface as you go downstream. And those are the conditions that define this difference between uniform flows, basically meaning that the depth of the flow is constant along the length, and that the slope of this doesn't change, of the bed doesn't change, versus rapidly varying flows where there's some big transition in the flow regime, typically because in this case there's a difference between the depth of flow here and the depth of flow here. They're clearly not the same, right, as you go downstream. And so we will deal with these kind of a binary binary classification, if you like, between these two regimes. Non-uniform flows, which would be gradually varying flows, and rapidly varying flows. It doesn't really matter what those are right now, but the basic requirement for these are that the slope of the water surface and the slope of the bed are different. That's it. So if that's the case, then it classifies it as a non-uniform flow, which we'll spend relatively less time dealing with. And the definition of a uniform flow is that the bed slope is constant. So it's a single, it's a line that's oriented in some orientation. But most importantly, the slope of the water surface is exactly parallel to this. And so in other words, the slope of this surface and this surface have to be the same. And if we think of that in terms of the terminology that we've used for Bernoulli's equation, if you remember, we talked about the hydraulic grade line as being the sum of the elevation. Well, actually, this would be the elevation right here. So, yeah, actually, look, this would be the total elevation here would be this. This pressure would be zero because it's on the surface of the water, and it's moving at some velocity. So this would be the hydraulic grade line. This would be the location downstream. This would also be some magnitude where this is the elevation, if you like, elevations 1 and 2. Again, this is on the free surface. So this magnitude is equal to the elevation. The thickness of the pressure is 0. So P over gamma equals 0 on the surface. And so this hydraulic grade line would be exactly parallel to the free surface of the water, which is also parallel to the bed, which we've stated is the requirement for uniform flow. And since this height isn't changing upstream and downstream, we know from continuity that the velocity 1 times the cross-sectional area 1 has to equal velocity 2 times cross-sectional area 2. Cross-sectional area 1 is just equal to y upper times the width, and the cross-sectional area 2 is just y downstream. If we've said these are both constant, then by definition the velocities have to be constant, and therefore v squared over 2g has to be the same height above this. And so it's a long way of saying that the energy grade line, EGL, has to be parallel to the hydraulic grade line. The hydraulic grade line is coincident with the surface of the water, and that's also parallel to the bed. So those 4 conditions are basically met, and you see that in that diagram. So we're only going to talk really about this condition where we have this behavior, uniform flows. And what we'd like to know, for instance, is how we calculate what the flow volumes are in a channel, given that we know something about maybe the slope of the channel and the conditions of the material surrounding the channel. So that's going to be our task today. It's a little different. So what we will, I'm not going to even talk about that. We'll come back to that, depending on how much time we have. So we're skipping through all this interesting stuff on why the flows get to be looking like hydraulic jumps. And we'll come back to it I guess we won't get through all that today, right? And we'll talk about uniform flows, because they're the kind of staple that we might be interested in. And the basic idea is this. So we'd like to be able to figure out if we have a flow in a river along some kind of bed, and if you look at the cross-section of this cross-section might be exactly what we're looking at, where we said before that we can classify this in terms of this perimeter and this cross-sectional area. I'll just do it as A. We'd like to be able to figure out exactly what this, basically we'd like to figure out this. How fast is water, what volumetric flow rate is water coming down through this? And so what we'll do is we'll make some assumptions. And it's a little bit like pipe flow. We know that in a pipe, if we looked at, for instance, the velocity profile across a pipe, we know that it's this parabolic velocity profile where it's zero velocity at the walls and it's some maximum in the middle of it. Well, you could imagine that flowing in a stream is probably similar to that. The velocity, if you look at a stream, you'll see these little eddies with sticks floating around it right at the bank because the water is basically kind of stuck there and it's being held back by friction. But in the center of the flow, you'll have the maximum velocity. And so if you look at the flows, either, I guess this is in terms of vertical section, the velocity at the bottom you'd think would be small or relatively, or either zero or small, because it's kind of stuck there. And as you get away further from the base of the flow, it'll be faster. And so if you look at contouring the velocities as you're flowing into the page here, you'd think that the velocities in the middle would be largest, which would be this amount here. And as you get progressively to the sides, around these areas here, you'd expect it to be relatively small. And so this would be, so if you like, this is slow, and this is fast. The slow might be zero. It probably isn't zero, because what happens, I think, in this is that, not I think, what happens here is you get this boundary slip, this kind of boundary layer effect, where there's some finite velocity occurring at this thin area just due to boundary layer effects. But the bottom line is that what we do is we take this distribution, which is really nonlinear, and we assume that it's an average, whatever that average would be. And you know, if you take the area under this and divide it by this length, the average would probably be something like this, right? You can imagine that being the average velocity. So that's basically what we do. And so this would be velocity average, and so the velocity average times the area of the cross-section is equal to the volumetric flow rate. That's really what we do. And so we ignore the fact that it has this kind of distribution, just like we did in pipe flow, and we make some assumptions. We don't need to worry about this. We'd also make some assumptions that the shear stress that's retarding flow, you know, same as the shear force that's applied on this bag by friction dragging across the table, water flowing past the banks will have the same thing. Maybe if it's going at zero velocity at the top and going at a higher velocity here, then you'd expect that the shear that's applied into the page, right? It's a shear stress that's applied into the page might vary like this, but actually we're going to just assume that it's uniform along the side, which is really what we did on pipe flows as well. Okay. So that's the basic precepts of what we'll deal with. So what we'd like to do is be able to figure out exactly what the flow rate is. And so what we can use is we can go back to using balances of forces and momentum in the system, basically a bit like Bernoulli, but we'd like to use it, we could use Bernoulli. Basically Bernoulli is a conservation of momentum equation. But what we can do is we can take a section of the flow, so this is the upstream face, this is the downstream face. We're looking perpendicular to the flow. The flow is in this direction. And what we can do is we can isolate this block of water. And we can look at the forces that would be applied on this. And so we know that from conservation of momentum, if we resolve things, we can resolve them in x and y, but we could also choose to resolve them along the direction of flow, which is probably easier in this case. So what we can do is we can resolve them along this, not in the horizontal direction, but in the direction of flow, which we'll call x, which we'll tilt this to. And we can write the momentum equation, right? This is our sum of forces is equal to mass flow rate times the velocities. This is an easy one to deal with because we know the mass flow rate in and the mass flow rate out have to be the same, steady state. And we also know that if this height is the same as this height, then the velocities v1 and v2 have to be the same as each other as well. Because, and so this cancels out. So this is 0. This doesn't matter what this is, and so this is the case here. So the forces have to just sum to 0. So what we can do is we can look at the forces that get applied on this. And so we can look at the forces on the upstream side. The forces on the upstream side would just be this triangular pressure distribution. The forces on the downstream side would be exactly the same triangular pressure distribution. And the resultant 1 and the resultant 2 would be exactly equal to each other. And they're opposite directions. So the first component are the forces between the upstream and downstream components. And then the only other components we have to balance are a shear force, which is applied on this base, which we'll call tau w, and the component of the weight. This is the weight. This is some angle theta, so this is also equal to theta. And so the magnitude of this component parallel to the bed is just w sine theta. It acts downstream. Shear stress is upstream, so they're the opposite of each other. And so we have this expression here. And so we can just rearrange this in terms of this component, and we end up with this expression just by rearranging it. The weight of the water, the inclination of the bed, the perimeter. So this is a shear stress, and if you imagine, if I kind of draw this in perspective, see, oh, it's not a bad drawing there. You notice I'm getting much better at drawing this? It doesn't look so shaky anymore. No one's saying anything? Perimeter. Area. So perimeter and the length of this is here. So in other words, the perimeter times the length is the area that this shear stress is applied on. Right? So if you multiply the shear stress by an area it's applied on, you get a force. This is also a force, as these are forces. So this is just the perimeter times the length, which is just a force. And so we end up with this expression here. We note that for very small angles of inclination, theta, which this will be, then sine theta is basically equal to the slope of this base. So S0 is just equal to the slope. Yeah, I will draw it on here. Right? So think of basically, this is the length along here, or the length in the horizontal plane. It doesn't make much difference. And this is, let's call it delta y. So S0 is equal to delta y over L. So kayakers think about going down a tough river. I guess it's 300 feet per mile is the gradient of the river. So this is the slope of the bed as it goes from upstream to downstream. And so we end up with this expression here. So you have shear stress defined as this. What we can also do is we can make some substitutions. We know that the weight of this is just going to be the volume. So weight is equal to the volume times the unit weight of water. And the volume is just going to be the cross-sectional area times length, right? And so if we substitute this into here, we get this expression here, and we just rearrange it so that this now is, this equation here is basically just rewritten, where we've substituted for the magnitude of the weight and rearranged some things. This, of course, is hydraulic radius. This is equal to a length over length, and so this is all we're left with. So hydraulic radius, the unit weight of the fluid, and the slope of the bed define the magnitude of the shear force that's applied on the system. So the only other thing that we need to do now is we'd like to be able to relate this shear force, or shear stress, to a magnitude of velocity. And we haven't talked about this in any great detail, but this Darcy-Weisbach formula, you can imagine getting this from Bernoulli, where you just basically take, if you rewrite Bernoulli as P1 over gamma minus P2 over gamma equals V1 squared minus V2 squared over 2G. In other words, if you just have horizontal flow, the elevations are the same, you have no losses in the system, then you end up with something which is a function of v squared over 2g. You have something which is a pressure change, and of course if the pressure changes from some magnitude upstream to some magnitude downstream, that has to be countered by some shear stress on the side of the pipe. And so you can think of this pressure change here as basically being a shear stress that's applied. And so this expression here merely links a magnitude of pressure to a velocity through an assumed loss coefficient, and it includes the, if you multiply both sides by gamma, I know I always get sidetracked doing this, so this, whoops, this and this go out. Gamma is equal to rho g, and so the g's go out, and so you end up with a density in here. So that's kind of where it comes from. But the bottom line is, if you equate this and this to each other, you end up with this relationship here, which allows you to get the velocity as a function of a bunch of parameters. And if we don't worry about what this term is, but treat it as a constant, then we can define the flow velocity in our open channel as a function of some coefficient times the square root of a hydraulic radius and a slope of the bottom of the channel. If we multiply this velocity, so if we realize that the magnitude of this coefficient is something a little bit different from this expression here, this is named from Chezy, who's a French scientist. The Manning formula and Chezy formulas are basically the same, but they're just modified that this coefficient is now taken as some number which is found experimentally to hold. And the bottom line is that the final expression you get is that the velocity of flow in the system is equal to some coefficient, which depends on whether you're working in SI units or English units, some friction factor, which is called the Manning coefficient, which is this lowercase n value, which you can think of as maybe a reciprocal friction factor, a hydraulic radius of the flow section, and the slope of the steepness of the gradient of the river. So it's, again, you end up with just a formula. So that's the end result. You won't be asked to reproduce any of this other stuff, but we have a formula to be able to get the velocity of, average velocity of flow in the system. If you want to get the volumetric flow rate, then volumetric flow rate is just average velocity times cross-sectional area. So this term here is just multiplying velocity times A, right? So that's it. So what it allows us to do is be able to calculate what the average flow velocity is, or the volumetric flow rate, so long as we know something about the behavior of the material that comprises the banks, the cross-sectional area of flow. So of course, if we need to know the cross-sectional area of flow, we kind of need to know the height of the flow as well, which sometimes isn't so obvious. And these other two parameters, okay? So it's just a formulaic way of being able to get flow rates. And so in the same way that we talked about kind of pipe networks where you might have flows in parallel different pipes, you can also deal with the same if you're looking at flow in rivers, where you might have portions of a river which would have maybe a Manning coefficient. Well, let's talk about Manning coefficients. So these scale with this value of this parameter which describes how the resistance to flow. So I suppose for all things being equal, the velocity will be highest when you have a small number of Manning coefficient. So a small Manning coefficient means presumably you have glass-walled boundaries to your open channel. And so if you look at these experimentally determined values, then they come in a whole variety of sizes for natural channels, for floodplains, channels that are excavated and left with open banks, and also the channels that you would have taking Colorado water all the way to California in usually concrete-lined canals for irrigation. And so you see, what can we see here? Glass. Don't have very many glass channels in reality, but the smallest of these Manning coefficients is for glass channels. And as you get progressively rougher walled, then they become larger, nothing more. They do not change with Reynolds number, so they just conform to the idea that we said before, that if you look at the Moody chart and friction factors, you have these different regimes. So we're always in this regime where we're turbulent, right? So they just become a constant number. They don't change. And I suppose for smoother values in the Moody charts, for smoother pipes, also the magnitude of the friction factor, I guess, is also small as well, right? I think. Can't remember. Doesn't matter. Anyway, so in terms of using this, you could imagine that if you had a channel, for instance, that had different values of this Manet coefficient, where it was different if you had, for instance, trees on the side of your channel and open in the middle. So if you have a flood come over the banks and it starts running through trees and houses, then you'd probably expect that the Manet coefficient would be larger on the sides than it would be in the central part, for some reason. It doesn't quite conform to these numbers here, but you get the idea. There's no reason why it should be uniform throughout, because you might have different components. If you have a very wide channel, you could imagine that this value of hydraulic radius, which is an important feature in calculating flow rates or velocities, also starts to become constant as you get larger and larger, wider and wider channels. So if the channel is very wide compared to its relative depth, then at some stage the magnitude of this hydraulic radius ultimately approaches just y, right? The depth of the channel, and depending on how wide it is. And so you can use those approximations as well. If you have a compound channel, you can calculate the equivalent hydraulic radius, as we talked about calculating equivalent hydraulic diameters, by using the sums of all the components which make this up. So clearly, in this part of the channel here, A1, you'd have a flow going into the board or out of the board towards you. And so you can calculate the flow rate merely by summing up the components due to the flow in channel 1, the flow in channel 2, and the flow in channel 3. The flows, all we're doing is we're saying that Q total is equal to Q1 plus Q2 plus Q3. And so you need to, it's quite evident. The Manet coefficients could be different in each of these. The slopes are probably going to be the same, right? Because I think that they have to be the same. The areas will be different in each of these, but also importantly, the hydraulic radii that you use should use the areas and, importantly, the wetted perimeter, right? And so the hydraulic radius for A1 is going to be this perimeter divided by this area. So you don't include the part between them, right? Because those things are going at the same velocity. Water's next to water from each channel, and they're just moseying down the flow, and therefore there is no wetted perimeter here, right? So this is the perimeter for 1, this is the perimeter for 2, this is the perimeter for 3. But the areas, of course, would be inclusive all the way up to the surface. And I guess the other thing that we can also figure out is that if you want to have, well, we don't need to do this, but if you want to have the highest flow rate for any given case, the highest flow rate will come from the largest possible hydraulic radius that you'd have for that particular system. So the Manet coefficient might be the same. This is just a scaling value depending on using SI units or English units. The slope of the channels will be the same in any case. So to maximize the flow in any given channel that you're designing, you might want to use the largest possible number of hydraulic radius that you could get. And so for some specific shapes, the largest number, the largest magnitude of hydraulic radius that you get for a rectangular shape is where the depth is equal to half the width. For a triangle, it's a right-angled triangle of any depth that stands like this, where it's just sitting like this. I guess it could be over on the side as well. It wouldn't make any difference. For flow in a pipe or a culvert, it's a pipe that fills the culvert, not one that only partly fills it. And if you have a hexagonal pipe, then again, it's one that half fills the hexagon up to here, and you'd have this. So don't know that you necessarily need that, but I think it's just a curiosity that you can imagine that if you want to get the largest flow in your system, the most efficient channel, you do it by either maximizing the hydraulic radius or basically minimizing the perimeter, because you'd expect to have the shear strength in this. Right? This is the frictional stress. Same thing. And so that's it. So it's nothing more than that. And so the idea is that if you want to be able to do this, it's just a plug and chug here. So here are a couple of examples. Yeah, well, we'll go through one anyway. And so if we want to be able to apply this, we want to be able to use this expression. It's in English units. So the value of K is equal to, or kappa rather, is equal to 1.49. I guess the other thing is to note with this, if it is in either of these cases, these expressions are unit specific. I think they're the only unit specific expressions we've talked about in this class. Certainly the petroleum literature is replete with every single expression seems to be unit specific, but these certainly are. None of the other ones we've talked about are. And so if you're using English units, the results come out in feet per second, and if you're using SI, they come out in meters per second. So you have to be aware of that. And so, of course, then the magnitudes for radii, lengths, and areas you should use are feet or meters as well. Obviously, the slope is dimensional. It's a length per unit length. And so for this particular case, it drops 1.4 feet every 1,000 feet along its length. It's lined with smooth concrete. And so we need to know what that would be in terms of a Manet coefficient. And I suppose smooth concrete might be this, don't know. Again, it's just like a friction factor. And what else do we need to know? So we need to know the cross-sectional area, and we need to know the hydraulic radius. And so the area is going to be equal to basically this area, this area plus the components on the side. So it's this is the middle part plus this height times this length, which you can just get from the tangent, and this gives you one of these, and so doubling that magnitude will give you two of them. So this is the second part. The wetted perimeter, do they calculate it, is just going to be this length plus this length plus this length, so you can get the wetted perimeter. From that you can get the hydraulic radius, which is this. You know that the slope, the inclination is 1.4 over 1,000. You need a value for this. I'm not sure what we use. I know what we just pulled off. Does anyone see what they use? Oh, is that it? No, that's the slope. Here, what do they use? Yeah, they use the same as us. And as a result of this, just by plugging and chugging for either smooth concrete or rough concrete, I guess this is this one, you end up with a value that comes out. You've used feet in here for the area, square feet. You've used lengths for the perimeter, and the number comes out in terms of CFS, cubic feet a second. And so that's it. It's just a recipe. And so it's nothing more than that. There are a couple of other examples that go through this as well that, I'm not sure you need to go through. It's just the same basic idea of being able to use this. In this particular case, you're given a flow rate. You're told that the lining is weedy, and so you can calculate the Manet coefficient for that, and you can write your expression in terms of a known value of flow rate, a known value of Manet coefficient. It's in imperial SI units, so this has to be 1. And so long as you can write the area, and I guess you know this here, what's it asking for? What's the depth of flow? Yeah, so you can write the area and the hydraulic radius in terms of the depth of flow, and you know what the slope is, and you can figure out from this, right? So you just write it in terms of the depth of flow, and that's it. So that's open channel flows. So that's all we'll talk about. Basically straightforward. I don't think you need to know anything about the derivations of those expressions, but you need to know how to be able to use basically these components. So this is the most obvious application of this. Okay? So, well, we could go back 50 pages and talk about it, but yeah, maybe we'll just talk in overview. So the other interesting, any questions on that before we head on? Let's go back to this. So the other behavior that we had here is if we wind this back. So this is, obviously, this is not the same kind of flow that we had before. So this is a hydraulic jump. You can imagine it's a river. But you have this interesting behavior in that you have water coming in here. Whoops, didn't mean to do that. And presumably we could apply continuity at this point and at this point. Since we're not accumulating fluid, it's kind of in a steady state form. And so if you multiply the cross-sectional area of flow here times the velocity and equate it to the cross-sectional area of flow here times the velocity, then by definition the flow velocity here has to be much larger than this by the ratio of these two heights, right? Basically the same amount. So the question is, why is that occurring, that it can flow in that particular way? And it turns out to be the case that basically the water, because it has, can I replay that? Because it has this extra degree of freedom, it can flow either quickly at a very shallow depth, or it can travel very slowly at a much deeper depth. It can choose either one of those equally well. So the analog to that would be if you have, say, other instabilities or unstable processes are, if you take a ruler and you lean down on it, it'll buckle. The mechanism by which it fails is not by shearing itself apart, but it just bows. So when you push down on it, it can bow on the left side or it can bow on the right side. Very difficult to predict which one it would be. It's the same as if you have a mound and you have a ball bearing that you put on that mound. If you drop the ball bearing on the mound, it can fall off this side or any of the other sides through 360 degrees. And it's basically at a point where a whole bunch of different paths that it can go on will give it the same reduction in potential energy, and it can choose those different paths. So water flowing downstream is basically the same thing. It's flowing, and it's at some metastable point, and if you change something in it, it can switch either between this perfectly admissible flow here, which is fast and shallow, or an equally admissible flow, which is less fast and less shallow. Less fast and more deep, I guess, in some respects. And so the basic idea behind that, without going into it in any great detail, is the fact that it all relates to the Froude number. And so it's kind of epitomized, I guess, in this little figure here. We've talked about the Froude number. Oh, I don't need to write it out. I guess it's written here. And the Froude number is just the ratio of the flow velocity, which is occurring, relative to the wave speed. Right? And so the wave speed, of course, is if you drop a pebble in, the velocity of that celerity wave, the ripple will travel away from you, is the wave speed. And it's a function of the depth of the water and gravity, whatever planet you're on, right? And so if you think about dropping a stone into a pond, Treasure Lake, for instance, and looking at the velocity at which this comes out, the velocity is given by the celerity waves. It's the same velocity as a tsunami travels across the wave, across an ocean. It's just the depth of an ocean might be 1,000 meters versus a stream which is relatively small, and so it'll scale with that. If you imagine that instead of being in a lake, that the water is traveling underneath a bridge and you drop that pebble in, then if you kept on dropping a pebble in and saw where the new outline of the ripple was, so you drop in a pebble every second, dot, 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 like a tap dripping, and you looked at where the waves had gone from each of the previous drops that had gone in the stream, you'd see that there'd be a whole bunch of circles still. These have to be circular, but they'd be non-concentric. They wouldn't be in the same place. They'd be offset. So they would be circles, but they'd actually be offset so that they are kind of bunched. This is a shorter distance here compared to this. If you make the stream go even faster, then it's basically like the Mach cone and the speed of sound. So if the water is coming down here at the same speed that the wave can go up here, then actually this would look like, what would it look like? It would look like this. Dot here, and there'd be a circle, and there'd be a circle, right? So this is exactly where the velocity of the stream is equal to the velocity of the celerity wave, right? Vc. And so what's happening here is if you could think of this in the same way, the information that's coming from the fact that you've dropped this pebble on never reaches upstream. There's no communication. The upstream portion of the river doesn't know anything about what you're doing because there's no information that's transmitted upstream by a wave being able to travel there. And so the magnitude of the Froude number, which is the ratio of the velocity of the stream relative to the wave number, when it's equal to 1, it's right on this verge that there's no information that goes upstream from the point that you drop this in. As the Froude number is greater than 1, then it will look like this. These will all be swept downstream. If it's less than 1, then it will look like this or like this. And so it's probably no surprise that it's the Froude number that actually is the index between these two different behaviors. And at a Froude number of 1, you have what's called critical flow, in which case the pebbles being dropped in would look just like this, if you look down in plan view. And there are two other states that it can go from that if you, for instance, constricted the flow. So in other words, if you imagine putting a sluice in here that would stop this from being able to get to this height, then it would reach two new heights. One would be a subcritical height, which would be upstream, which would be higher. And one would be a supercritical height, which is downstream, which would be lower. And these would be for a Froude number greater than 1 and a Froude number less than 1.